Hey, what's up, chem peeps? What in the heck are we gonna do in this video? In this vid, we wanna be able to describe the role of intermolecular and intramolecular forces in the solution process. All right, so three big things that we're gonna do in this vid. One, we're gonna explain the solution process in terms of solvent-solvent, solute-solute, and solvent-solute interactions. Two, we're gonna identify which forces, the solvent-solvent forces, the solute-solute forces, or the solvent-solute forces, are stronger in an exothermic solution process. And then lastly, we're going to come back to those same three forces, solvent-solvent, solute-solute, or solvent-solute, and think about which of them are stronger in an endothermic solution process. All right, so before we dive into this video, let's think about making a solution at the molecular level. Recall that we have solvent, which in many cases is going to be water, agua, and then you have a solute. It's what you add to the solvent. It's what gets dissolved. Here we go, adding the solute to the solvent. Oh my goodness. I'm going to pause it for a moment for you to recognize then, as we make our solution, it's taking the solute, putting it in the solvent, boom, solution. All right, and in this video, what you really want to be thinking about are the intermolecular forces of attraction that we have throughout the solution process. And the best way to understand sort of how the intermolecular forces tie in is to think of the solution process as occurring in three steps. Step number one, the solvent-solvent attractions must be broken or overcome. This is an endothermic process, or you'll have a positive delta H. Take a look at the thrilling image on your screen and in your notes. Focus on step one. Your solvent, in most cases water, you need to separate that. You need to overcome some of those intermolecular forces, hydrogen bonds that you're gonna see in water. And that process is endothermic. To put energy in to overcome the attractions. So coming back to this thrilling animation, I'm gonna start with the solvent again. Pause. Recognize that water, which is commonly our solvent, is a polar molecule. And there are very strong hydrogen bonding intermolecular attractions between those molecules. So your first step is to put some energy in to overcome those attractions and make room for your solute. Step number two, the solute-solute attractions must be broken or overcome. This again is an endothermic process where you'll have a positive delta H. You're putting energy in to separate or break apart the solute-solute attractions. Same image, now focus on step two. Your solute, in the example that you saw earlier, sodium chloride, you need to overcome the electrostatic attractions between oppositely charged ions, those ionic bonds, in your solute. Again, you're separating those things. You're putting energy in to break those attractions. So once again, step two is going to be an endothermic step. Next, think about your solute. There are attractions between the sodium ion and the chloride ion, and we need to overcome those attractions so that I can get this to dissolve in the solvent, water, and make my solution. And that brings us finally to step three. Recognize that the solute-solvent attractions form to make your solution. And just like the formation of a bond or other attraction, that's going to be an exothermic process where the enthalpy change is going to be negative. Oh, so now we're taking our separated solvent, our separated solute, mixing them together, and new attractions form between the solute and the solvent particles. And that step always going to be exothermic. Energy is going to be released. And then step three, attractions form between the solute and the solvent. In this case, they are ion-dipole attractions. And the formation of those attractions, just like the formation of a bond, is going to be an exothermic process. All right, so big takeaway here. Once you recognize that the solution process occurs in three steps, keep in mind that Hess's Law can be applied here to determine the overall enthalpy of solution, simply by summing together the enthalpies of the individual steps of that process. If the overall solution process is exothermic, that means that more heat is given off upon the formation of attractions in step three than was absorbed in step one or step two. But keep in mind, you can also have an endothermic solution process. All that means is more heat was absorbed in step one and step two than was given off upon the formation of attractions in step three. So let's take a look at a couple of practice questions. Pretty short and pretty sweet. I just want you thinking about the 3 steps that go into the formation of the solution and recognize whether we have absorbed more energy in step 1 and step 2 or released more energy in step 3. Your first example, lithium chloride. Heat of solution here is negative 37.1 kilojoules per mole. In other words, this is an exothermic solution process. Step 1, energy must be put in to separate the solvent particles from one another. Positive delta H. Step 2, energy must be put in to separate the solute particles from one another. Positive delta H. Step 3, attractions are formed between the solvent and the solute. Energy is released, an exothermic process. Now, importantly, because the heat of solution overall is exothermic, what that means is more energy was given off upon the formation of the solute-solvent attractions than was absorbed to break apart the solvent attractions or to break apart the solute attractions combined. Let's take a look at another example. For potassium nitrate, the heat of solution is positive 34.9 kilojoules per mole. Let's think about step 1. Energy must be put in order to break the solvent-solvent attractions. Positive delta H. Always. Step 2. Energy must be put in to break the solute-solute attractions. Positive delta H. Endothermic process. Always. And then lastly, solute-solvent attractions form to create our solution. Energy is given off in an exothermic process, negative delta H, always. But notice how this differs from the previous example. The overall enthalpy of solution is positive. What does that mean? Overall, more energy went in to break apart the solvent-solvent attractions and solute-solute attractions than was released upon the formation of the solute-solvent attractions in that final step. You have a fantastic day.